Okay, this is a video on using Lagrange multipliers to find the best quadratic unbiased estimator for sigma squared in the multiple regression model. Now it's 6 pages, so it's a little bit longer, but it's a fun video. And this is it's taken from James Scott's book, Matrix Analysis for Statistics. And what I do is I take his example and fill in much of the in-between steps. So this is what we want. We're in the multiple regression setting where the error term is normal, 0, sigma squared I. So each off, they're all independent because of the it's only diagonal, and there's n observations. So we want to find A such that this is an estimate of our sigma squared, where A is symmetric, sigma squared is unbiased, and it minimizes the variance. Okay, so let's just jump right in. So let's look at what does it mean to be unbiased. So let's just take the expected value of our estimator. Well, substituting in for y, for each y, multiplying this out, matrix multiplication, okay, noting that this is a number, so this is a 1 by 1 element. So this and this are actually equal. If you take the transpose of this, which is 1 by 1, so it's okay, those are the same, so it's 2 times this. And then when we distribute the expectation in, this is a constant, expected value of that 0, so that goes away. And this, since this is a number, we can take the trace of it, because the trace of one number doesn't change anything. And when you take the trace, you can rearrange the matrices in here. It has to make sense. And then we'll retake the expectation. So that's what I do here. This comes down, that's 0. I rearrange the matrices to this, and then take the expected value. And this right here is it's the variance of that estimator. So we have that stays the same. And this expected value, the A comes out, and then that's just sigma squared I. Well, that's a constant, so it can come out front, and A times I is just A. So for unbiasedness, this is the case. Well, how can this be unbiased? We want it unbiased for sigma squared. So in order for this to happen, the trace, this has to be 1, and this has to be 0, but those are known constants. So this here has to be 0. So to be unbiased, these conditions must be met. Okay. Now, and Lagrange multiplier, you have to have it set equal to 0. So this is already 0, and then so we'll subtract 1 over here, then it equals 0 when we get to that step. So now let's look at the variance, because this is the thing we want to minimize. So let's write it out and see what it looks like. And this right here, and then we expanded it. This we did on page 1. So you substitute in for y and multiply it out. Now we need to take the variance of each of these terms. Okay. One note that this is a constant in regards, this is our variable. And so any variance we do, this is going to drop out. So we're just taking the variance of these two. Now, this is the sum, so it's the variance of the first plus the variance of the second plus 2 times this covariance. So we'll look at each one of these individually. So we'll call that 1, 2, and 3, and we're gonna deal with this one first. And so the covariance, and we're not dealing with the 2, just the covariance, is this. Well, this matrix can be pulled out front, and that's what we do here. So now we're looking at the covariance of this. Okay, So the covariance is, it's the, and this will just keep out front. So it's the expected value of this times this minus expected value of this times expected value of that. And that's what we have here. Okay. Well, this piece right here is 0. So this goes away and we're left with just this piece. And that's what this says. So when now we're going to look at this piece here. Okay, this is a quadratic form. Okay, so that's a double sum of all the elements, and now that's what I'll write right here. So this E is that E, it's a vector, and this is a number. So this is the formula for the quadratic form here. And then so this number gets multiplied by each of these elements, which is what I do here. So this is element 1 of that, and that's element n, and it's times this constant. So now when we take the expected value of this, we take the expected value of each element. And this is a vector. So when the ij's are not equal, then they're all independent, so that expected value, each one of those is 0. So now let's say that I and j equal, but not equal to 1. So that's ei squared, but this is the expected value of this is still 0, so that's 0. And then let's say they all equal 1. So that's the expected value of the third moment of ei, which is also 0. And that same argument goes for each element. So each one of these the expectation is 0. And since this is 0, 0 times any matrix is 0. Okay. So in here, we use the fact that the expected value, the first moment is 0. That's the mean. Second moment we said was the variance. Third moment is always 0. And the fourth moment is 3 times sigma fourth. Now this fact, the video just before this one, I looked at all the moments of a standard normal distribution, and that video applies to this if you want to see more detail about this step. Now before we move on, I want to look at this. So the expected value of 4 different error terms, okay? If they're all equal, that's the expected value of the fourth moment, which we said was 3 sigma squared. So all of them, these are the same. So now, if 3 of them are the same and 1 is different, pick 3, then that odd one is always expected value of, would be 0. Then if we look at 2, let's say 2 and 2 are the same, k and l and I and j, that's the expected value of ei squared and ek squared, and those are independent, so you can break them apart. So that's expected value of that second is sigma squared, the second one would be sigma squared, and so it's sigma to the fourth. And that's if 2 indices are the same, but they're not equal to each other. That's this case. And then if they're all different, then expected value is 0. So this is the setting that I'm going to work with in a second. Oh, no, that is... oh, that's coming up. So now let's look at the first term in that variance, which is this. So then we have to, the property says take this out to the front and then take the transpose to the back. And that's what this is. And the variance of E is sigma squared I. So the sigma squared can be out front, and anything times I is itself, so this boils down to this number. Now, let's look at number 2. But before we do that, we need to we need to look at something first. The expected value of this quantity. Okay, so that's squared, so that means that's squared. Now this is a quadratic form, and that's a quadratic form. So let's substitute that in. And since it's the product of linear combinations, you can, bring those together. So it's the quadruple sum of this, and that expectation goes into this. And so when we were looking at the expected value of the 4 E's, then this is what plays. It depends upon what these indices equal. And there were 4 cases. So that's when they were all equal. That's this case. So they're all equal. So that's a squared term, AI squared, 3 sigma fourth. And then there were 3 cases where the 2 pairs were equal, but that the pairs weren't equal. So that's this case. So just plug in. We go over I and K, I not equal to K, and this one is I and J not equal, and this is I and J. So this is the 3 cases, and every other expectation is 0. So now let's look at these individually. So this will stay the same. This one, we're missing the I not equal to K. So if we put that case back in here, then we have to subtract it out. And the same here. If we put in the I equal J case, and here the I equal J, actually then those would equal, so it'd be 2 times that, and we have to subtract out 2 times those. So that's what this next step is. So this carries down because that goes into the front. That goes to the front, but since we now I and J equal, we have to subtract out this one case. And here, when we let I equal J, those 2 actually are the same, so it's 2 times it, but then we have to subtract out 2 of the case where they equal. Well, this, and that cancel, leaving just this and this. So here's what we have. Now, this, right, so this double sum could be separated into this, and then this is just the trace of A, and this is the trace of A because the indexes are a dummy index, and then this can be shown to be the trace of A squared, so we get this number here. So to find the variance, and now this is the number 2 in the formula, this was just so we could get here. So this is equal to the expected value squared minus the expected value quantity squared. This we just calculated. This we calculated on a previous page to be this. So combine those and we get this, because those cancel. Okay. So then conclusion is that the variance, which what we're going to try to minimize, we said was the variance of this plus the variance of that plus the variance of this, is this. Okay, so now we're going to take the derivative of this function. Well, adding in our Lagrange multipliers. So a couple notes, and this is, remember the condition that this is 0, and so this is the matrix after multiplying that out. So we have to have a Lagrange multiplier for every one of those, set it equal to 0, add them all up, set it equal to 0. So what they do in the book is they multiply this times a lambda matrix, and so we get this. Now we could take the Hadamard product of these two, because then we'd get a lambda parameter to each one of those, and then we would have to take the sum of every element. But what they do in the book is they multiply this out, and you end up with this matrix. So this diagonal element is actually take one of those times, each element here times its respective element there, and then add them all up. That's what this is saying. So if we take the trace of this matrix, then that's the equivalent of taking the Hadamard product and add them all those up. So the trace of this is that double sum. And so these are all the conditions that have to be 0. So now when we set up our Lagrange equation, so this is the variance we want to minimize, and then we have to subtract out the two conditions. So this has to be 0, this piece here, which is the same as that trace of that has to be there, and then the trace of that has to be 1, so you subtract 1 and multiply it over. So now we take the partial with respect to A. So since the video is so long, I'm not going through the derivatives of matrices, but this boils down to this. This is this piece, and that's this, and that's this. Okay, so now simplifying, multiplying that in, set it equal to 0. Now this equation we're going to call star, and we want to pre and post multiply by this quantity, where this is the more Penrose generalized inverse. Okay, so we get this equation. Okay, so so there's the pre and the post, and I expanded the more Penrose here and here and here, and then I just kept it tight where we pre and post multiplied by this quantity here. Okay, well, remember that one of the conditions was that is 0, this is 0, this is 0, and then the definition of the generalized inverse says this is x. And this right here is interesting. It can be shown that this is symmetric. So if you take the transpose, it doesn't affect it. So we take the transpose, and then if we take the transpose of this, we get that. Well, that is x, so it's x transpose. And then this piece here is just x. So it boils, we get this, that this equals that. Okay? Now we want to substitute this back into the star equation. Okay. Well, then we get this. Okay. So these two pieces actually were at the end of the previous equation. You can factor out a lambda from both of those because this is that. And then the first part of the equation, when you multiply, doesn't change really. Okay, and then we can solve for A. And so basically this goes to the other side, this goes to the other side, we substitute in this for that, and we factor out a lambda, and that's what this is. Now this A is what this is, and then of course we divide by this everywhere, and we get this. So now we're going to shorten this formula up, we're going to call this H. Alright, and then what I'm going to do next is show that H is 0. Okay, we're going to call this equation double star. So so we're going to call this H, double star. So if we use double star back into star, so we're going to put this A in here, here, you know, wherever there's an A, okay, which is this. Okay, so this is A, and then we stick it in here, and here, and then there's no A here. But this piece here, so it can be shown that when you multiply this x times this, it's 0. So this piece drops out when you multiply. And then this piece, this is beta transpose x transpose, and that x transpose times this ends up being 0. So it drops out. Okay, and so then this piece here will cancel with this piece. And we get, and it boils down to this. So this h can be taken to the other side because it's 0. So we take it over here, and then we get the positive, and then we divide by this. Or, you know, since that goes in, we get sigma squared, and then we divide by sigma squared. So we end up with this. Now we're going to call this triple star. So if we post multiply triple star by x beta, then we get this, and then here is the post multiply. So that when we take this in, then when we go into here, by the definition of h, remember it's a transpose where'd it go? Oh, it's on the back page. Anyway, you can show, then when you multiply this in, we get the relationship of x transpose a x, which is 0. So this ends up being 0. So we multiply it into here, we just get this. Now, this is negative, so we subtract it to the other side and factor out an h x beta. Then here it's just I. And then here, since this is a constant and that's a constant, it's a constant times I. And it all equals 0. So now let's factor out an I. Right? And then I times anything is anything. So we get this. And then, but this is times a constant. So this constant is times every element in here. But this is not 0. Because we have a 1 here. So if this is a number, then this is still a number. But, you know, if we get 0 here, then this is still a number. It's 1. So this can be divided to the other side. Well, that says h x beta is 0. Okay. Now so we're going to use that fact. So now let's pre-multiply by x beta transpose, and then because the video is getting long, you can use the same argument to show that this is 0. Okay, so by 1 that we just showed here, and 2 we just showed here, and the definition of 3, h is 0. Okay, so now we can do that. So this, we just showed that this piece is 0 and that piece is 0. So this is 0. So h must be 0. So now to use the last piece of information, we're going to take the trace of double star, which is this. Now, the trace of that we said was 1. So then we multiply that piece up and divide by this piece, we get lambda is this. But this trace is n minus r, where r is the rank of x. Now we substitute this piece back in double star, and we get this. So those cancel, and we're left with just this quantity. Well, that is the sum of squared errors divided by its degrees of freedom. And that's usually what we use as the quadratic estimator of sigma squared. So anyway, I hope you enjoyed this. To me, it was a pretty fascinating problem, and I'm so glad I got to share it with you. If you enjoyed the video, like it. If you want to subscribe and not miss the next video, please do. Thank you. Bye.